Hello everyone, welcome to the second video of the lecture 1 of EC 573 Advanced Embedded Logic Design Winter 2022 semester. In the video 1, we discuss about the need of mapping the algorithms on the hardware platforms, and that is the problem statement of the AELD course. Now we will discuss about the what are these platforms which are being developed by the VLSI industry and how the evolution of this platform has happened. So before going into the details of these platforms, we first understand the difference between the system on board and the system on chip. So system on chip is a single platform that can be used to implement functionality of your entire system instead of using the several different chips on a board. For example, on the left hand side, you can see here is the system on board where you have the together, multiple chips connected via external interface. While on the right hand side, you will see that the system on chip where entire functionality is mapped inside the chip. You don't have the external connection or don't have the multiple chips. So for example, if you look at the Bluetooth SoC, where you have the you have the product which has the Bluetooth capability. You can develop such product via system on board or via system on chip. In case of the system on board, what you will do, you will have the complete PCB. You have the one chip for the processor. You have the another chip for the Bluetooth, and you may have the another chip for the interface like UART, Ethernet, depending upon your requirement. So this is called as the system on board. On the other hand, in case of the system on chip, you have only one chip where your Bluetooth, physical layer, the processor and the interface are everything is integrated inside one chip. Okay, so that is the difference between the system on board and the system on chip. Okay, so what are the advantages of the system on chip? The first thing is that you get the better performance because the inside the system on chip, the propagation delay is less. Also, the gate delay is less because internal transistor have the lower impedance. Efficiency, because you are operating at the lower voltage compared to the external interface, your power efficiency is better, and the capacitance effects are less. Again, you are not driving the signal outside the chip, the signals are limited inside the chip. Light footprint, your size and the weight is reduced. If you see the devices are getting more and more small size, in terms of size they are getting smaller. For example, 10-15 years back you used to buy a separate FM receiver, right? But nowadays FM receiver, you don't need to buy a separate FM receiver, it is now a part of your mobile phone itself. So you can do the better integration. You don't need to buy multiple device. Your integration becomes better, and also size of the devices goes down. Higher reliability. You can see that since the signals are limited or are there inside the chip, it is very difficult for someone to hack the chips, or it is very difficult for someone to interfere with your signal. So the reliability is better, and the cost is good because you need to fabricate fewer number of chips, so that means your cost efficiency is better. Okay, so these are the advantages of SoC, and we all know why these SoCs are quite popular and they are part of our everyday life. But then what are the limitations? Now inside the SoC, everything is fabricated and put inside the chip, so it is very difficult to change something. So you have very less flexibility. For example, in our laptop and desktop, which is a system on board, you can always add the external RAM or external SSD memory to improve the performance. But inside the system on chip, you can't, once your memory is finalized, on chip memory is decided, you can't add it. You can add it externally, but it is no longer a system on chip board. It's a system. It's no longer a system on chip. It's a system on board. Also, future upgradability is a issue. So these are the application specific. So once you design a Bluetooth SoC, it will work as a Bluetooth SoC. Even if there is a new protocol comes in the Bluetooth in the future, it will not support it. You need to replace it with the new devices. Same case for the Wi-Fi SoC or any other application. For example, in case of the FM also, it will support a certain frequency range. But if there is changes in the future, for example, FM works from say 90 megahertz to 108 megahertz. Suppose in the future you change it to 90 megahertz to 110 megahertz, but then your current device will not support it. So it's a application specific. Also, it's a complexity. In the system on board, you can have the different engineers works on the different chip and one engineer at the PCB level. But when you are designing the system on chip, you need an engineer who has a good knowledge about the various aspects of the system on chip. You can't separate out the work. Furthermore, it is the interference from one chip to another chip is there is a possibility of the interference there, because you may have the multiple components working at the different clock frequencies, and they can interfere or lead to the degradation of performance of some adjacent chip. So you need a good well-trained manpower who can take care of these issues. Okay. So these are the things which are there in the limitation of the SoC, and people are VLSI industry is trying to address this issue. But we need to understand what are the issues that may arise in the near future. So if you look at the evolution of your electronic product or the VLSI industry over the last few years, you will see that over the years, industries were facing the similar challenges and pressures, like next generation electronic system must improve the performance and offer the higher level of integration. For example, if you take the mobile phone, every year we want a mobile phone to be faster with a lot of additional features. Okay, but at the same time, we don't want to pay a significant cost, and also the power consumption or battery life should be as less as possible. And fortunately, our VLSI or electronic industry is able to address these issues quite efficiently. We are getting the good quality mobile phones, laptops with so many features over the time. But the things are changing. Now, there is an additional requirement from the consumer as well as the VLSI engineers or VLSI designer. These requirements are flexibility and scalability. So let's look at what is the flexibility and the scalability. So for example, in case of the scalability, so this is the requirement from the VLSI engineers or VLSI designer. Suppose you are working in the VLSI industry and you are developing the two products, same product for the two categories, one for the low cost and one for the high cost. And suppose that your manager told you that for low cost, use the ARM processor, and for the high cost, use the Qualcomm processor. Now, as a designer, you need to study the architecture of both the processor. You need to map your algorithm or your system efficiently on each of the processor. So you need to write a code in a different manner for every processor. And that's a lot of work. So what designers are telling, why can't you design a scalable platform so that the same platform can be used for the low-end devices as well as high-end devices? Obviously, there will be change in the resources when you go from the low-end device to high-end devices. For example, you may have the instead of single core, you may have the quad core processor. Instead of in the low-end devices, you may not have co-processor. In the high-end devices, you may have a co-processor or better GPU. Also, in the low-end devices, you may your instruction set might be your instruction set in the low-end and high-end devices will be more or less same. So the same code can work on both the architecture. So the VLSI designers are expecting such scalable architectures. On the other hand, consumer is expecting the flexible architecture. What do you mean by flexible architecture? Like when you go from 3G to 4G, 4G to 5G, you need to buy a new mobile phone. It is just that even though your screen is working properly, rest of the body is working properly, till you need to replace the mobile phone. So the people are asking, consumers are asking, why can't these mobile phones are upgradable or flexible so that I can add the new technology without replacing the blocks which are working properly. And you can see that this is called as also called as a hardware reconfigurability, and the corresponding concept in the software is software reconfigurability. And in the software reconfigurability or software upgradability is quite easy. You can, on the same laptop, you can go from Windows 7 to Windows 9, Windows 10, and Windows 11. On the same mobile phone, you can upgrade your Android version. You can upgrade your Android apps or iOS apps. You can easily upgrade it. So software upgradation, the problem has been solved quite well. Why can't we have the similar solution for the hardware? So this is what the demand is, and that's why people are expecting the VLSI industry or the electronic industry to develop the flexible and the scalable hardware platform. So there is a significant evolution or work has been done in the last few years to come up with the scalable or the hardware platform. So you can see that in the beginning we had only the small processor which does the limited amount of tasks. Then with the requirement of image video processing, especially on the mobile devices, now you can see that the processor comes with the GPU as a co-processor. Again, in the more complex system, along with the processor and the GPU, you have the additional hardware like ASIC, that is the application specific integrated circuit, or FPGA, that is the field programmable gate array, to perform the or to accelerate the more complex tasks. So in the beginning, they added these things as external chips. So this is the system on board. So where you add it via external links, and you can see that all the issues of the two multiple chips or system on boards are there in this one. So the natural evolution from the system on board to the system on chip, where you have the single chip on the same silicon, you have the processor and the ASIC or FPGA hardware. We need to know that the processor are the sequential devices while the hardware can does the task in parallel. So in the beginning, you can see that this is the PowerPC, which is the processor developed by the IBM. So in the beginning, they started with this PowerPC processor, which is implemented on same silicon as the FPGA and ASIC. So this is the system on chip solution, and this was developed by Xilinx. Okay. Then over the time, ARM processor becomes popular. So Xilinx came up with the new architecture, which is called as the zynq architecture, and it is called as the APSoC, that is the all programmable SoC. In this case, they have replaced the PowerPC with the ARM processor. So it was a dual core ARM processor. So this is the architecture we are going to use in our lab, and this programmable logic is the FPGA logic. So this processing system, which is the ARM processor, programmable logic, which is the FPGA, you can see that they are there on the same chip. This is the system on chip solution. Then next version is the multi-processor system on chip. So here you have the dual core processor, here you have the quad core processor. In addition, here you don't have the GPU, here you have the GPU, here you don't have the real-time processor, you have the real-time processor. So you can see that it's the same platform, but you add the additional features. The PL is the same. So you can see that this is called as a scalable platform. For low-end device, you can use the APSoC. For high-end device, you can use the MPSoC. So these are again are developed by the Xilinx, and similarly you can see that the Intel is also developing the similar platform. So just to give you the background, in terms of the FPGA, there were two companies. One was the Xilinx and the second was the Altera. Now Altera is few years back is taken over by the Intel, which is the processor company, and they are trying to integrate the FPGA with the processor. The Xilinx is now being taken over by the AMD, which is another big processor company, and then AMD is trying to integrate the FPGA in their processor. Then for the edge devices, there are other companies are like, for example, ST Microelectronics developing their edge AI devices. So for microcontroller for IoT application, NVIDIA is a big company which is trying to develop the edge devices. And for the application specific, for example, for 5G, Xilinx has extended this MPSoC to the RFSoC, where you can have the ADC, DAC up-down conversion on the same chip. So multiple solutions are being developed to meet the scalable and the flexibility requirement of your consumers as well as the designer. And we call these SoCs are the heterogeneous all programmable SoC. So you are aware about what is SoC. All programmable means everything is programmable. Your FPGA, which is the field programmable, it's not ASIC no longer, it's FPGA. Your processor is a multi-core, it is software, it is a programmable, and it's heterogeneous. So you have the processor, you have the real-time processor, you have the GPU, and you have the FPGA. So you have the different kind of devices together. So this is how the evolution of the hardware platform has happened to meet the requirement of your next generation services, which needs a distributed computing. In this course, we are going to focus on zynq architecture, and in case you are interested in the research and all, we can in this kind of devices we already have in the lab, so you can use them in your research work. So this completes the various next generation hardware platforms which are being used in the industry as well as academia. In the next lecture, we will discuss what is the features of the AELD platform, hardware platform like this platform, which we are going to use in the AELD course.